So I think we can start. We're glad to have Gabor Kun, who will talk about his joint work with Andrea Tom about non-amenable groups admitting no sofic approximation by expander graphs.
Thanks, Alex. It's a pleasure to be here. So at least this is a positive effect of these days. As you may imagine, the talk is not really about a problem we managed to solve, but we have, I hope, quite nice partial result towards it. So we view our result, what's quite good explained in the title, that even though we didn't find any non-sofic group, but at least in the subuniverse of, say, strongly ergodic or good mixing structures like non-amenable groups and expander graphs, we found examples which have no sofic approximation by expander graphs. So at least in this subuniverse, we succeeded. So the talk will contain a lot of proofs, or at least proof ideas. On one hand, such an excellent audience is a great victim of telling these things. On the other hand, most of these proofs are about understanding sofic approximations of Kazhdan groups, or more precisely, almost automorphisms of such sofic approximations, and how stable or what kind of stability results we almost have for this. So I expect that this will attract the audience as well. And on the other hand, in this seminar, it's quite hard to say many new notions. But in any case, I just introduced the basic players. If the slide goes, yeah. So expander graphs will, of course, play a crucial role in this story in sofic approximation of Kazhdan groups. So the definition I write here is just the usual, but I allow bipartite graphs. So I'm interested in graph sequences of finite deregular graphs, where the eigenvalues of these graphs are in the interval minus d lambda for some lambda less than d, what's the first eigenvalue. And of course, we have the equivalent and sometimes more useful definition of Cheeger's inequality, that for any subset of size less than half of the vertices, the number of edges leaving this subset is at least a constant h, the Cheeger constant, times the size of this subset. And well, the regular participants of this seminar have seen application of expanders in most of these subfields of mathematics listed below. And the expander graphs we will study here will come from sofic approximations, so they will belong to permutations, so they won't be really undirected graphs as expected from expander graphs, but they will be digraphs which are labeled by some group elements, but this won't lead to any confusion, or in case it did, please just ask me what's going on, or Andreas will help me out. So sofic groups and sofic approximation is the other main topic of this talk. So all the groups that appear in this talk will be finitely generated. I'm afraid some theorems may not be true otherwise. So we say that a group has a sofic approximation if there is a sequence of finite sets and functions from the group to the symmetric group over this finite set, such that these two conditions hold asymptotically. One is asymptotic homomorphism, that for any two elements of the group, if we look at the image of a point under alpha times beta and its image under beta times its image under alpha, then for most of the points asymptotically we will get the same point. And the other key condition is asymptotic freeness, that for any non-trivial element in the group, the number of fixed points in its representation by this permutation function will go, the number of fixed points or the proportion will go to 0. And we call a group sofic if it admits a sofic approximation. So to note that already the generators determine these functions phi of n. So it's enough to look at these generators, and the rest will be asymptotically unique by this asymptotic homomorphism condition. And this will also allow us to think of these approximations as finite graphs. So we just take this finite set of generators. We look at the permutations, what they give us for every n, and the graphs of these permutations, or the union of the graphs of these permutations, will be the Cayley graph, will be the H set of this graph. And then sometimes we forget about this direction and edge labeling, sometimes we don't, but I hope this won't be a problem. And a few examples of Sophie groups, most of them you already have met, and somewhat important example what I think didn't appear so far is the notion of LEF groups, locally embeddable into finite, which are very close relatives of residually finite groups, but somehow they crucially appear in our main results. So I wanted to define them. So we call a group LEF if for every pair of elements in the group, this asymptotic homomorphism I defined here will be 0. So this limit will not only be 1, but it will be constant 1 for every large n for any two elements, alpha or beta. Of course, the n depends on these two elements. Residually finite groups are the simplest examples of LEF groups, like SLDZ, D by D matrices with integral coefficients, and finitely presented LEF groups are in fact residually finite. So those interested in finitely presented groups only need not to distinguish between LEF and residually finite groups. And the other important notion for here will be amenability. Well, this is one of the nations in mathematics that has the most definitions. So one is that these groups admit a left invariant finitely additive probability measure. These are also great examples of Sophie groups, including solvable or more specifically abelian groups. And besides these basic examples, amenable and residually finite groups, there are a few constructions like direct product, free product, or amalgamation over amenable subgroups, but we don't have many more examples how to construct Sophie groups from existing ones. So even though we do not know if every group is Sophic, the zoo of our examples seems so far somewhat limited. And just to mention a few results what are known for Sophic groups and make their study interesting, they are. So the first one is Kaplansky's direct finiteness conjecture, that in a group algebra over a field, if A times B equals 1 for two elements, then B times A equals 1. This was showed by Kaplansky in maybe 59 for the case of the complex field, or say holds more generally for characteristic 0. And it also holds in case the group is Sophic, but there aren't many other cases known, rather sporadic ones. Next example is Con's-embedding conjecture that every group is hyperlinear. Since Sophie groups are In fact, hyperlinear, this also holds for sofic groups. So in case every group is sofic, that would make the life for many more people simpler. And next one, the Kerber-Lauterbach conjecture was explained by Andreas in more details, but in the one variable case, it says that every regular equation in a group has a solution in an extension of the group. We call an equation regular if the sum of the exponents for that single variable is not zero, as there are counterexamples. And so even if we may not be able to solve the equation in the original group, we want to solve it in a supergroup, like in case of fields, we may look for a solution of a polynomial in an algebraic extension of a field. For example, in the two-element group, we have no element x, that x square is the non-trivial element of the group. But if we embed the two-element group in the four-element group, then we already have two solutions. So we have such equations in mind, and these are known for sofic or more generally hyperlinear group. And another very useful notion was the sofic entropy introduced by Bowen, and it led to several interesting results. And of course, the question, as I mentioned, what drives our research is to find a non-sofic group. Well, of course, the question is if every group is sofic, but as our approach shows, we rather vote for the non-existence of the existence of a non-sofic group. So besides discrete group theory, I need to say a few words about measure preserving actions on probability measure spaces. So we consider an action of our group gamma, which is probability measure preserving on a space X. And we say that it's ergodic if it has no essentially invariant measurable subset that is neither a null set nor a conal set. So for any group element, if we move S, then by this non-trivial group element, then it will move it out by a positive measure in case the action is non-ergodic. The other is notion we use is, well, not so surprisingly, since we will be interested in expander graphs, is strong ergodicity. So we say that action is strongly ergodic if in case we have a sequence of almost invariant subsets, then they should be close to have measure 0 or 1. So in case we have a set that for every generator gamma moves the set outside of it by only a small proportion, an alpha proportion, then the measure of this set should be very close to 1 or 0. And using strongly ergodic actions is one way to define amenability, because amenable groups have no strongly ergodic actions unless it has an atom, or in case of probability measure spaces, it should be already finite. And for Kazhdan groups, exactly the opposite will hold. So this one possibility defined by for the definition of groups with Kazhdan property T by Kohns and Weiss, that is that a group is has Kazhdan property if every ergodic measure preserving action on a probability measure space is also strongly ergodic. So this again shows that amenable and Kazhdan groups have opposite nature, like water and oil. So only finite groups are both amenable and have Kazhdan property T. Definition is the standard definition due to Kazhdan. I assume you are very familiar with this, and so I won't recall it. So in terms of unary representations. And also may know the standard examples lattices in simple Lie groups of high ranks, finite groups, and also some Gromov type random groups with the right density belong to the family of groups with Kasdan's property T. And the theorem we will use to get our main results is one theorem that's proof of a nice conjecture of Bowen that states that if we have a sofic approximation of a Kasdan group, then it should be essentially a vertex disjoint union of expander graphs. It may not sound very surprising to those both familiar with Kasdan groups and expander graphs. So, any questions about what I said so far? Or I may go to the main results. Maybe I have run through a bit quickly, but you are quite educated. Okay, thanks. So let me go on to the main results. So somewhat surprisingly or maybe disappointingly, we study here direct product of groups. So in both of our theorems, the group gamma will be a group with Kasdan property T, and delta another group. In the second case, it's amenable, so it's really, as I said, mixing water with oil. And we have the set of generators in mind where for the direct product, we simply take the set of generators, that's the union. So we take the generators of gamma and the generators of delta. This doesn't really affect our theorem because just changing the set of generators doesn't change that the fact that we have a sofic approximation, and also being an expander or not doesn't depend on the choice of generators. So we define these graphs, what I call expanders in these theorems, using a set of generators, but if it's expander for one set, then so is it for the other, with possibly a different Chigger constant, of course. So the first theorem says that in case we have an sofic approximation by expander graphs, which are expanders with respect to the generators of the Kasdan property T group, then the other group will be LEF. So in fact, it's very close to be residually finite. If it's finitely present, then it's residually finite. And as I showed you on the previous slide, if we have a sofic approximation of a Kasdan property T group, then it will be necessarily by essentially a vertex disjoint union of expander graphs. So it's not a huge extra to assume here that we have not a disjoint union or essentially a disjoint union, but one single expander graph for every finite n. And the second theorem using the first one proves this a bit. So in this case, we will have an amenable group delta besides the group, the Kasdan group gamma, what will be our favorite, and we will spend most of our time analyzing this one. And in this case, we can say that if this product has a sofic approximation by expanders, then the amenable group should be LEF. And since there are many other amenable groups, this also means that for certain amenable groups, the product gamma times delta has no sofic approximation by expander graphs, even though the product is a non-amenable group itself. So it's what I promised in the title. So this answers a sub-question what was quite studied in the theory of graph limits and related to what's called local global limit, what's called by Hatamilovas and Szegedi, and also it comes from the color neighborhood metric of Bolobás and Riordan. In this combinatorial framework, they are not interested in the Benjamin-Schramm convergence or the local local distribution of the balls in the graph, but in the local colored neighborhood. So they look at all possible colorings of these, say, Borel graphs in a measurable way, and they take the outdoor space that contains all the possible colorings, and they take the local distance, the Benjamin-Schramm distance on this, and this gives them the local global distance and limit notion. So this is very natural in graph theory, where they want to understand things like colorings or independent sets. So that it was not known if in this notion what's basically close relative to the so-called weak containment of Abert and Weiss, if in this notion it's possible to approximate large graphs or group actions by finite ones. In fact, it's still not known. It's quite a strong notion of convergence if the irregular random graphs are convergent in the local global sense. So it's not an easy case, but the case or theorem, the second one, also gives an example to this. Any questions regarding the theorem since on this slide?
Yeah, may I ask you, I just listening to you, I feel like one should define, it seems like natural to define that a group has property tau, extending property tau to the case up to now, we always define property tau assuming the group is residually finite. Your work seems to suggest a generalization of the notion that property tau means having a sofic approximation by expanders. And
yes.
my question is, first of all, is it true that if the group is residually finite and it has sofic approximation by expanders, then it has some family of finite index subgroups which are expanders with intersection of the identity? Like, is it really a generalization of the notion of property tau of course, in the weak sense, property tau can be defined with respect to some family of finite index subgroups. So I don't expect it to be true for all of them. That's clear because the free group has property tau with respect to some and not all. And I assume that the free group, of course, can be approximated by expander. So, but assume the group is residually finite and approximated by expander, does it has property tau with respect to some family of finite index subgroups?
Yeah, so of course we don't know anything like this. We can state quite precisely what we do know, just going back a slide, in case of this theorem. So this doesn't use the full power of property T, but we only care about limits of sofic approximations. Say it's enough to have property T for the ultra product of any sofic approximation or for this particular one that appears in the theorem. And this is exactly what we need for that theorem and some of its lemmas to hold, or at least we cannot weaken it by an epsilon even, or at least I.
By the way, in these theorems, if instead of Kashdam property T, you will assume a property tau in the strong sense, namely property tau with respect to all finite index subgroups. The feeling is that that should be enough, not? You are here really using infinite dimensional.
Yes, so the proof goes that Well, the present proof is ineffective. So we take the ultra, at least at one point we need to take an ultra product, and well, one may of course think how to make it effective, and then well, it's not hopeless, at least I think so. It's possible to go. Right now it's ineffective, but well, probably it's we cannot discuss it right now or not even after the talk, but improvement is possible in that direction, I think.
Okay. By the way, what is the problem about random d-regular graphs that you said is unsolved?
Oh, just that we don't know if they are a local global limit of finite graphs. So it's a strange thing, but you fix, I don't know, you take d equals 3, you take the free regular graphs, for every n you take a free regular graph on n elements, and you do not know if this will converge like in this local global sense. For example, the independence ratio, it's unclear if it will converge or not. So it might be the case that, of course, it sounds very stupid, but it's not proved. So it might be the case that, I don't know, for even powers of 2, you have a different independent ratio than for odd powers of 2. It couldn't be proved. What was proved that the Bernoulli shift is not the local global limit of random graphs, because the independence ratio is too small there. This was Gamarnik and Sudan, if I remember well.
Okay, thanks.
More or less, this is, I think, what one may do, or what's the right ambition with this local global limit, because it's very ambitious. It captures most of combinatorics, including NP-hard problems, and so studying random objects is a reasonable direction, I guess. So any more questions regarding the main results before we go into the proofs? If not, then it's gone. So we've proved the first theorem first, of course. And so just the language is that we will consider these permutations in the Sophic approximation. And we will study the graphs that belong to the Sophic approximation of the Kazhdan group gamma. And we will think of the other group delta when studying the Sophic approximation of the direct product, that the elements of delta are almost automorphisms of the Sophic approximation of gamma, because these elements, of course, commute in the direct product. So we may think of them as an automorphism of these permutations or graphs, labeled graphs, we wish. And we say that an F, a mapping from the vertex set to the vertex set, is an almost automorphism if it's a bijection. And for the generators, it makes only delta times Vg errors in this commutation. So all but delta times Vg edges are mapped to an edge with the same label. And the first lemma was...
But it's automorphism of the graph, first of all, before talking about label.
Yeah,
almost automorphism is an automorphism of the graph.
Well, it's a labeled automorphism, almost automorphism, but it's not an automorphism of a graph. The graph, we don't require it to be an automorphism, but only a labeled automorphism, or an almost labeled almost automorphism. So for almost every edge but delta times Vg, the edge will be mapped to another edge with the same direction and the same label. Is this okay?
But I understand. But assume it doesn't, like if two edges are coming out of the same vertex, the image also should come up from the same vertex or not at all?
No, not at all. So the image might be any other vertex. So the simplest case is when you have, say, a transitive graph, say a Cayley graph, then of course every automorphism itself might be an almost automorphism with delta equal to 0. But here we allow some errors, so some proportion of edges might not be mapped to an edge, or might not be mapped to an edge with the same label.
Okay.
So maybe the next lemma will show why this makes sense. This is due to Simon Thomas, who also studied Sophie groups, namely, he showed that it's consistent that there are many universal Sophie groups. So it's essentially his lemma, but he used a quite different language. So this one says that in case we have an expander graph, meaning that we have a set of permutations and we look at the graph, what they give us, and we have a delta automorphism of this set of permutations for some small delta, or two delta automorphisms, then these two delta automorphisms should be either very close or very far from each other. That's of course not very surprising if we think of real automorphisms of a finite, say, vertex transitive graph, then, and we have this heredites from a set of permutations, then if the two automorphisms agree at one single point, then they agree everywhere. So not so surprising in this sense, but in case we have expander graphs, we can make this statement more qualitative. So the proof is that for these two automorphisms, we take the sets of points where these two agree, and assuming that this is not a too small or too large set, there are many edges leaving this set, meaning that there is a point x in the set that one of the permutations, I should write pi of I here, so one of the permutations pi of I maps it out of the set. And since this pi I of x is not in the set, this means that C of pi ix and C prime of pi ix are not equal. And so either C or C prime does not map the pair x pi ix to a pair which is still labeled by the same permutation. So for every single edge in the boundary of this set A, we can calculate some loss in the automorphism of C or C prime. And if we sum these up, we just get exactly this lemma that we look at this set A. If it's small, then just calculation with the Cheeger constant gives that these inequalities, and if it's a large set, then we get the second inequality. So is this clear? It's probably a good probe stone if the definitions were clear in this slide. So somehow our point is that if we start to study these delta automorphisms, then they have a nice tendency to cluster, that we will have somehow clusters of these close to each other or very far. So they seem to have a nice structure for us, where this depends on the Cheeger constant. And once we have this nice structure of almost automorphisms, of course, we try to gain something like stability. It's, of course, not to expect that close to any almost automorphism, we will find a real automorphism, but we can get something pretty close to this asymptotically. So this lemma says that we have, for a Kazhdan group, well, I mean that we have fixed the set of generators for this Kazhdan group. We have a capital K that in case we have a delta almost automorphism and a possible much smaller delta prime, then close to this delta automorphism, if n is large enough, we can find a delta prime almost automorphism. So a much better almost automorphism that will be close to it in the sense that it will be at most a constant times the error of this first automorphism. So even though we are not able to find a real automorphism, if n is large enough, we can be arbitrarily close to this desired kind of stability, or we may say that in some limit structure we will have stability like in the ultra product, but so this will be the next very and most useful lemma for us. And before seeing how to get this lemma, just a few thoughts about almost automorphisms. And this will make it more clear by kind of having a disjoint union of expander graphs as a sofic approximation will make sense. So we consider a bijection from the vertex set to the vertex set, and we want to see look at the graph of this bijection, what's a V element subset of V times V, and we want to see how close it is to be or how good almost automorphism it is. On V times V, if we can define the action of the permutations coordinate-wise. So if we had D permutations on V, then we still have D permutations on V times V that act coordinate-wise, and this gives us a graph structure on V times V. And what's good to note is that this function we have started with is an epsilon almost automorphism for an epsilon, if and only if the edge boundary of this set, the graph of the bijection, is at most epsilon times the number of vertices. So somehow this comes from the fact that if we have an element xvx in this set B, then an edge leaving this set going to some y and node B of y will be just a point where we lose something in the automorphism, where we lose something in the almost automorphism of this. So somehow this means that we can translate of having an almost automorphism to having a small boundary in the graph V times V. So this is the key observation for us. And once we have it, and may I jump to the next slide?
Sure. Yeah.
Okay. Then we use the following lemma that's also from this paper where this disjoint union of expanders result is proved. It looks pretty long, but the essence of it is that we have a subset T in a finite graph with small boundary, and we want to find another subset close to it with very small boundary. We want to find another set of vertices U that has much smaller boundary. And for this, it's sufficient to know that in this finite graph, for a large R, where large depends on this alpha, how small boundary we want to have in the end, the balls look the same as the balls in the Cayley graph of the original Kazhdan group gamma. So this means that the property that close to any set, we find another set with small boundary close to it, is a local property. So already the having isomorphic balls to the ones in the Cayley graph of the group gamma can force this. So, of course, I don't want to prove this theorem, this lemma, but at least this is kind of the middle lemma in this result, the disjoint union of expanders result. So I think it shows much more how the proof goes on than the theorem itself. And also it turned out to be much more useful for us.
Yeah, just a second, maybe you can leave it for...
Yeah, it's the time to stop.
Can digest this.
1 second.
Any finite...
I have my voter. So it's phrased in the strange way that in case the boundary of this set T is very large, so it's a constant times the set itself, then this U might be the empty set and it's meaningless. So we only care about the case when the boundary of this T is small, where small depends only on the Kazhdan constant. So this is somewhat hidden here, but the interesting case is when we have a subset T with a small boundary and we want to find a U close to it, but very small boundary, meaning alpha times U. And then this, how close we are to the Cayley graph of the gamma, how large R balls are isomorphic to it, will really just appear here depending on alpha. So that's also an ultra product argument as of now. So any questions to this?
Yeah.
So the moral is that close to a set with small boundary, we can find a set with very small boundary. And I guess it's also clear that it helps a lot to get a disjoint union of expanders. So the next is that once we have such a great tool that we can improve an almost automorphism, we can already define a group structure on these clusters that are almost automorphisms. So we choose an epsilon and the delta depending on epsilon that's much smaller, say we divide by something like the Kazhdan constant. And then we take the clusters of delta almost automorphisms where two almost automorphisms are in the same cluster if their distance is at most epsilon times V. And these will, luckily for us, form a group. First of all, we can define the product that we take two delta almost automorphisms. Their product won't be a delta, but a two delta almost automorphism. But we know that we have this improvement lemma that we can improve a two delta almost automorphism to a delta almost automorphism. Moreover, in the process, we won't go too far. So we will find one close to it. And since this is so close, we can also check associativity and everything we need in order to define a group structure. So in the end of the day, we have that these clusters of delta almost automorphisms define a group structure for us, finite groups. So that's a quite good sign for the future. And of course, the elements of our group, this delta, act as almost automorphisms, meaning that every element of delta, if n is large enough, then it will meet this barrier epsilon and delta of epsilon. So for a large n, every element will act as an almost automorphism. And this will give us a Sophie approximation, but not the one we started with, but the one that we can define on this finite group of clusters, that it's simply if n is large, then an element of delta can be mapped in this group, and it just acts on this group by the left multiplication. And then it's easy to see that if we pick any pair of elements in this group delta, then for a large n, they both can be mapped in this group, and there won't be any error in this Sophie approximation. So for this for any finite set for large n, we will have a homomorphism if we restrict ourselves to this finite set. So in the end of the day, this is exactly what an LEF group means.
It seems like you don't really need the delta is a direct factor of the group. It will be enough if it will centralize gamma.
Well, yes, you use commutativity. You only use that these pairs commute, it seems. Yes. Though in case of a Kazhdan group, yeah. Yeah, so we only use commuting pairs here.
So
any
like,
questions regarding this?
If you have some Sophic approximation of some bigger group, which are expander with respect to some partial generators, then the centralizer of these partial generators is LEF, right? That's really what you're proving here. You haven't used at all the fact that this is a direct product, if I'm not mistaken.
That these pairs commute, so I can represent these elements of delta as almost automorphisms in the Sophic approximation.
That what? Yeah, so that's,
yes,
yeah.
Exactly. So any more questions or comments? If not, then I just go back what we proved. We are close. It's the next theorem easier. So we have proved the first theorem that in case we have an approximation of a direct product by expander graphs, then the other one delta, what's not the Kazhdan group, should be an LEF group. But in this theorem, we assume that we have expanders with respect to the Kazhdan group gamma. So it's not a disjoint union or essentially disjoint union of expanders, but we really have expanders. The gamma generators give us expander graphs. And now the next theorem is about the case when we have an amenable group besides the Kazhdan group, and all the generators together will give us an expander. And then again, the amenable group should be LEF. So now we need to reduce this case to theorem 1. Yeah. So we consider this Sophic approximation by the product, and we know that the gamma edges induce a subgraph that's essentially a disjoint union of expanders. And of course, we may assume that it's a disjoint union of expanders. We just change very few permutations a tiny bit. This won't change the original condition. And the first observation is this claim 1 that if we look at these expander components, now really disjoint union of expander graphs, then the action of the elements of delta is essentially well defined on these components. what I mean by this, that if we pick a random element, then for all but a small proportion of the elements, the image of the points in the component of this element will go to the same component, but again for a very small proportion of them. So it's asymptotically well defined almost everywhere how this delta acts on the components. And the proof of this simply uses the expansion and again the commuting pairs, that in case we have an element in a component and its neighbor gamma x, x and gamma x, and alpha x and alpha times gamma x are not in the same component, then alpha gamma x cannot be gamma alpha x. Simply these two elements won't be the same component. So for every such edge where the neighbors are mapped to different components by an element alpha, we will have some error in this commuting in the Sophie approximation of the commutators. And since all these components are expander graphs, if there is no overwhelming majority in a component where most of the elements are mapped, but they are mapped to two or more different parts, then for all the boundary between these, we will have some errors in some commutators. So this will sum up to too much. So that's why we can define an action of delta over these components. So I guess it's quite visible what we are going for. We wish to kind of factor out by these components. And we will be able to do this soon. So the next observation for us is, once this is well defined, that we have a very large gamma component. One of these expanders will have a positive proportion of the vertices for at least a subsequence of this Sophie approximation. And this is the point where we need some, well, we may avoid it, but I think it's more educational to use a non-standard argument, that we take the measure, that a finite probability measure space for every n, namely the atoms will be these expander components, their measure will be proportional to the size. And we have that the action of delta is well defined or essentially well defined on these, and hence the group delta will have a well defined action, a probability measure preserving action on the ultra product almost everywhere, of course. There might be a null set of errors. And this is, since this was a sequence of expander graphs we have started with, this action will be strongly ergodic, or where it will have a spectral gap. But our group delta is amenable, so this sequence should have an atom. And this atom only can come for a subsequence, what is large in the ultra filter, and for some delta, there are large subsets of proportion, at least delta, that belong to this. So we made a big step that even though we don't have a gamma expander as in theorem 1, we have a large gamma component, a large expander in this situation by this claim 2. Any questions regarding this slide? Yeah, so this is the standard way to use strong ergodicity, and this is the only point where we use amenability. And or the last slide, so we have a large component, and we will choose a subsequence in our Sophie approximation such that for every element of the group delta, for this large component the Cn intersection alpha Cn, I dropped these phi-n's a while ago, divided by C of n exists. Of course, we can do this by a diagonalization argument. And we know that the action of the elements of delta is well defined on these expander components. This means that the image of Cn under an element alpha might be essentially Cn or disjoint from it, but it cannot be the half of it or anything in between. So it so this for this subsequence, for every element we have a 0 or 1 in the limit for this ratio. And then we look at the elements for which this limit is actually 1. So they are, so to say, Cn is asymptotically invariant under this subset of elements, delta underline. Of course, this will be a subgroup, and it should have index at most 1 over delta. And so we look at this, the group gamma times delta underline. Then we have a Sophie approximation of this group on a somewhat smaller set, this set Cn, where we have already the permutations that belong to elements of gamma. And besides this, every element of delta underline has a representation of it, and asymptotically maybe with maybe it only has essentially, and we need to fix the minor error. So this group delta underline will be LEF by the first theorem, and since it's a finite index subgroup of another LEF group, or no, it has the other way, delta should be LEF as well. So this is what finishes the proof. And so thank you for your attention. So.
Thank you very much. Some more questions. May I ask something which just not directly related, but I've completely forgot about this notion of LEF. Now, this LEF is if a group is LEF and finitely presented, then it must be residually finite.
Yes,
now,
exactly.
But I assume that there are examples of groups which are not LEF, right? That's not as difficult as sofic.
Oh, yes. Oh, yes. I don't want to say stupid, but maybe the Baumslag solitaire group, the first sensible one, 2 3, or what is of this property. So this where V inverse equals A cube is, I think, LEF already.
What is
LEF? Sorry.
Which one?
This Baumslag solitaire group.
Baumslag solitaire group is not LEF?
That's
no.
Gunnar says something.
Oh, you mean the Baumslag solitaire?
I think there are better answers in the chat than what I have in mind.
Oh, Gunnar says, I see. What is Gunnar? What is RA?
Residually amenable, but of course it's not. I mean, one needs to know how exactly it is residually amenable, but.
But if it's this,
yes, it's finitely present. Sorry. Yeah, I wanted to have something which is really not approximated by anything. Yeah. It's a good example.
So no, I'm now confused. So it is not it is LEA.
It's not LEF.
It's not LEF because it is finally
it's
presented.
LEF, but not LEA. No, the other way around. It's LEA.
Yeah.
It's locally embedded into amenable.
But not LEF, yeah.
But not LEF. I see. I see. Uh-huh. And what are other example of non-LEA which are finitely generated, finitely presented, and not LEA? Now I'm confused. LEA, which is finitely presented, does not have to be residally finite, right? I mean, this is an example, like the bound-like solitar. So what is an example kind of to think about of a group which is not LEA? You remember, Alon, I see that you're writing that there are
yes,
examples.
so I think there is an example of SLN over the ring Z1 over P, and like an amalgam over itself, like take an amalgamated product with itself over a cyclic subgroup. There is a short paper that proves it's not LEA.
Not LEA, I see. Okay. Okay, some more questions.
So I have a question. I think I know the answer, but still will ask. So
You're welcome to answer it. Yeah.
So you cannot really replace this amenability condition by saying you have amenable action with some good properties on some, no?
So the only place where we use this amenability is on this slide that this action is strongly ergodic and so by amenability there should be an atom.
Didn't you use amenability at the very beginning that you said that the component of gamma are expanders?
So that uses Kazhdan's property T. So the expander component kind of theorems are about Kazhdan's property T only.
Oh, I see. You don't need it, that the other side is amenable.
So in the first theorem, we have no amenability at all. And in the second, literally, this is the only point where we use it, that this kind of limit space, in this case, the ultra product, will have a strongly ergodic action, and then by amenability, it should have an atom. So somehow we need this claim to.
I see.
Yeah.
Okay. Any more questions? Okay. If not, let me just say that in the next few weeks, we are going to take a shift in the seminar, and instead of looking at sofic and discrete approximations and stability with respect to permutation, that was the topic in the last month, we will go to approximation and the stability with respect to the unitary matrices, and especially with respect to the operator norm that we hardly touched up to now. So in some sense, it will be like a new start. So those of us who feel like they got lost, from next week, it's going to look quite different than what we had so far. Okay, see you all next Wednesday.